I have to let you know that you're being recorded if you say anything, whatever. If you don't want to be recorded, then have a nice cup of don't talk. If you talk, if you come up here and stand in front of it, you've implicitly said, I'm okay with it.
Yeah.
Okay. All right. The way this usually works, since we got 3 new people, and then David, he knows that I lie like a rug, generally for simplicity. So the way I've been teaching this class for however long I've been teaching it is, the idea is with the maker in mind, people who want to go out and build stuff and have some fun. But I'm a firm believer that the better you understand how and why something works, the more adept you'll be at getting things to work right.
You dropped that card.
And so I go behind the scenes on a lot of stuff and tell you a lot more than you need to know a lot of times about, for a maker thing. But it's there. So, like I said, I tell lies for simplicity's sake. We talk about wires not having any resistance and things like that, and then we occasionally step back and say, oh, well, here's the real truth, and what are some of the ramifications when you're doing something. We also do quite a lot of stuff in code. Most of what I do here, I use an Arduino platform as the base, because you can buy one for 20 bucks, and anything that is valid that I'm teaching up here that will work for that will work for anything else, for the most part, as long as you're not trying to do real-time stuff on like a Pi. But yeah, go ahead.
The term Arduino, is that a new name for something that used to be called a PLC?
No. So an Arduino, it's an Italian company. They came out 6-7 years ago. They took an Atmel 18 mega 328p microcontroller, put it on a circuit board, and you write C code. Well, you can write any kind of code as long as you have a compiler for it. But you tell it what to do. It's levels below a PLC. PLC, you've abstracted. A PLC is a programmable logic controller, if you don't already know. It's not ladder logic, you're actually writing code. If this, then that. Then you have to compile it, push it onto the thing, and then it'll run. The Arduino itself is a card about that big. They've got the integrated development environment, the IDE, is free, and you can download it directly from arduino.cc. The Arduino cards plug into your PC via a USB cord, and so you can talk to them. They've got serial over USB. There's all sorts of fun stuff you can do. But most of what I'm talking about here is probably usable with a PLC. The PLCs generally are a lot slower.
Oh, this was 20 years ago.
Well, they still are. They're still slow.
Siemens S7.
Yeah, Siemens, Allen Bradley. It's another company. What is it?
Honeywell?
I don't know if Honeywell still makes them. They may have.
Allen Bradley.
Allen Bradley. They.
You can find better, but you won't pay more.
Exactly. And then, they're safety rated, so you can use it, but only these modules are safety rated, and as soon as the software's not. So
Is that again for like higher voltage, higher amperage kinds of applications?
No.
PLCs are basically for, correct me if I'm wrong,
industrial process control.
A production line, industrial control of machinery. We had one company, we were in, it was paper machinery. Okay, it loads this up, there's a sensor on it. Okay, is it the right size or not? Yes or no? It has to say, these are my decisions. Okay, it's going to go there. it's on the conveyor belt. The sensor sees it, pushes it down. Okay, now it's gone. Now I can allow something else to come down. It's inputs and outputs that are programmed. I mean, that's how to.
A highly distributed, localized, very limited logic control.
Yeah, you can spend a couple of $1,000s and only have a couple, maybe 100 I/O.
I was the technician, and then we had the programmers, and the one was really. They get burnout real fast, but I was with one who was really excited on testing the envelope of every component of it. Like, we had a vehicle that had to drive down this hallway, and a piece of machinery would hang down, and he had to program the sensor and block everything out. Like, there might be people walking in the background, and he just used a portion of the sensor to look for that arm. You could put a broom in front of it. It knew there was a broom. It knew there was something in front that had to stop. And he really read the book on each sensor. Wow, it can do this, and it was fun to work with this guy.
Yeah, most people don't, and their code is awful, and it's full of unintended consequences. And
I know all about those guys too, because I worked with another guy in the same company who was very much disliked by me, and before we were in a paper mill in Germany putting in another set of guided vehicles that worked on a sensor in the floor, and the Friday before he hops on the airplane to go home, he dumps in a new program, and the boss, the guy from the factory, calls you up and says, "You guys can't leave because it's doing these crazy things." He says, "Oh, well, I'm going home. Mike, you can stay here for the weekend and babysit the machines till I come back on Monday and fix it."
wow.
But they couldn't figure it out, but it was something as stupid as human error. The guys are supposed to unload the machinery, let it sit there until they called from the other end and says, "Hey, we need the vehicle back." And it goes there, and it's not at its charge port. And then every time it runs back, it jumps in the charge port.
Yeah, yes. All right. So we're going to get on with this tonight.
Yep.
So I'm going to talk about, if time allowing, I'd say that I try and keep the class to an hour, but sometimes it goes 3. Because it sends me down a rabbit hole, or we end up with a discussion, and so try to keep it about an hour. Tonight we're going to go over 3 different kinds of sensors, a PIR, string pots, and quadrature encoders, or encoders in general, quadrature encoders specifically. We'll go through both. These are related, so I'll start with them first. If you remember way back in the very beginning, we talked about, you weren't even here for this, we talked about resistive circuits. So if I have a voltage source here, and I have 2 resistors, R1, R2, the total resistance in this loop seen by current is R1 plus R2, R total. So we're going back to Kirchoff's voltage and current laws here. The voltage law says that the sum of all the voltages in a loop must equal 0.
Resistances. Volt.
Sum of all voltages in a loop must sum to 0. The sum of all currents in a node must equal 0. So one, Kirchoff's voltage law, Kirchoff's current law. So if I have an I here, what it comes down to is minus V. If I go in the direction of current, V1, V2, it'll look like this, plus to plus, minus to minus. Minus V plus V1 plus V2 equals 0. So loosely, V is equal to V1 plus V2, which any of you who've been doing anything with electricity for any amount of time know that's true. And then we go back to Ohm's law, where P is equal to IV and V is equal to IR, power, current, voltage, as a horrible R, resistance. So we know that V1 from that V1 is equal to I1 R1. V2 would be equal to I1
So that acts as kind of a
R2.
backup, so it stays on, but in theory, that should also do local processing.
And from there we can back out and figure out what our, so we've got multiple equations, multiple unknowns, you'll back it all out. But when you push this back and do the math, you'll find that the voltage at that point, this is called a voltage divider, V out is equal to V times R2 over R1 plus R2. Once you do all that math, I'm not going to run through all the math to get us there. So this is useful if you have a 5-volt source and you want to have a constant 2 volts out here somewhere for something to measure. Go through and do the math and you can figure out that this needs to be one resistance in ohms and this one needs to be another, and you'll have that. I'm going to do this in my head right now. I can't do this math in my head today. Now, there's a device called a potentiometer. It looks like this. This is the symbol. And this is, if you look at what this thing is inside, there's a solid piece of whatever it is. It might be a coiled wire that runs around of certain length. And then there's actually a physical wiper that runs along the edge. So you connect the two ends. If I put voltage here and I put ground there, now as I move this, I'm changing these values. This can go from 0 up to full resistance, and this will be going the other way. So you can think about the two halves of this being R1 and R2 right here. So when you're down here, R2's big, R1's small. When you sweep over this way, R1's big and R2's small. So by twisting these things usually,
this was a device that was added to the.
You'll most often see them looking like this.
It's fine. I don't know. I mean, I think our.
That is awful. And there'll be 3 leads coming off the back. And one of them to the 3. And as you turn this knob, it'll move. There's other ones that are called slide pots. It's got, looks like a switch, but you slide it. You can see those on like an old graphic equalizer, if you know what an old graphic equalizer is. Sound tables, things like that. So we talked about this a little bit a couple of weeks ago. This is called a string pot, a string potentiometer. There's another name for it, which is what you'll find it for in a called in a catalog. And I cannot for the life of me think of what it is right now.
So I just got a little repeater. A lot of people just get another Z-Wave device, and it'll act as a repeater.
It's called a string pot because it's got a string.
The repeater was 10 to 15 bucks.
And a spring.
And a spring.
Device that I might look
So what this is, there's a piece of clockwork in this.
Yeah, the link bulbs over on the pad that are individually addressable, and then 3.
You've got that thing. You've got a frame. You've got a wheel. And inside the wheel is a clock spring. And when you pull it out, it tightens up. And when you let it in, it lets it loose. If you ever use one of these things, do not let it snap. Don't let go of it, because it comes in, it slams, and it screws them up. They're useful when you want to measure distance on something, calibrate it out. That's actually what this was for. I've got 3 of them wired up to an Arduino at work. Actually, no, I have 2 of them wired up to an Arduino at work. We were moving a table up and down, and this was to measure the corners of the table to see how it was deflecting. With, I think the biggest load we put on it was 1,500 pounds, and it was a single little hydraulic cylinder pushing it up and down. a neat, it was a scissor lift type of thing. So what you get in here, so now we talk about, hey, this is neat, all right, this is clearly useful. As this thing, when it's all the way down here, the wiper's all the way on one end. When it comes up here, the wiper's at the other end. So you can say, oh, this is here, I think this one's 10 kilo ohms. I think this one's 10 kilo ohms end to end. So there you get about 10 kilo ohms. There you get about 50 or 100 ohms. And if I put current on that, put voltage on that, I've got the voltage divider and I can read it out. So here I've got my hot is red, my ground is black, my signal is green coming out of it, and I can measure this with an analog to digital converter and turn voltage into digits and know where my position is. I have to calibrate this, of course, right? I can say, oh, it's here, it's here, it's here. But it's relatively repeatable, and I say relatively, so this is one of the things you got to know when we start talking about how these things work and why they work the way they work. You've got this potentiometer mounted in here through this wheel. Like so, ish. So that's this thing. You see the box? There's a wheel here, and this rope wraps around this wheel. So number one, first problem you have is, well, the potentiometers tend to wear, and you're never going to come back. You know, you say you are in the exact same spot, but you're not in the exact same spot when you come back to zero. So you never want to use it at zero, and you never want to use it at full extension, because those will be slightly different every time. Part of the reason for that is there's no guarantee that this thing's going to wind evenly on this. You could have a wind go, you know, in an ideal world it would be this, but maybe one of them decided to come back across like that. And so cross-wound, like on a winch, right? When you get that weird coil thingy on it, and then it, so now when I've let it back in all the way, there's still tension on this, and it's in a slightly different position than it was before. Same going all the way out. When you hit the stops here, every time you hit that stop, you're smacking the inside of the pot, which means that wiper is coming over here and going whack, whack, whack. So you want to try and use them somewhere between maybe 10 and 90%, or maybe 5 and 95%. So yeah, these are great for position sensing. I think they might call them a linear position sensor. But you can do, the nice thing about a string pot is I can set this over here, I can run it over a pulley, and I can do that. And I can burn my finger if I'm not careful. So I hand that around if you guys want to take a look at it. That particular one, for the average maker, we probably won't use those. That's like a $50 component right there. Just that one is $50, and you don't see them for much cheaper than about 25 or 30. But they're good for what they're good for. Now, go
I
ahead.
think that's the first time I've had my hands on one of those, ever.
Ever?
I've used opticals,
Yeah. Well.
and linear opticals even, but
So when you get to the opticals, so we'll go to an encoder. An encoder is what you use in a mouse, or used to before they were lasers, right? You've got a wheel that maybe looks like this. That way, that way, that way, that way. And maybe it's clear, or maybe it's black, and those are clear lines. So like, if you imagine you took a piece of glass and you painted it black, and then scratched that off on it, so that you can see through it where those lines are. There's a couple of different ways to do this. So in a mouse, they used to have a wheel that looked like this. It was actually solid black in the middle, and It had a rail that ran around the outside. And you'd set the mouse ball would be here. Remember balls and mice?
Clean your mouse balls.
You got to clean your mouse balls. God, they were awful too. It would. There's a little roller right here that would get all skeezed up, and here would be an LED putting light off to a photo transistor here, and so every time it goes past, tick 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 tick. So. If I take an output there, every time this goes dark, if that goes dark, this goes up to 5 volts, dark. And when it's light, does that. Tick, 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 tick. Move it nice and slow. Tick, 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 tick. Move it fast. Tick, 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 tick. This is useful when you want to know the position of something in space. Another way you can do this is to put a magnet on this wheel and have a Hall effect sensor, or maybe a little tab that comes out so it comes around and hits some sort of a little switch when it goes around. There's 1.5 million different ways to do this. Some ways are better than others depending on what your requirement set is. You know, you don't use mechanical things if you can help it for things that need high reliability. But if it's only got to last and you want to be able to tweak it right there on the spot, then mechanical thing's the way to go. So this is useful because as it goes tick, 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 imagine it's the speedometer in my car. And every time that this window comes around is 1 revolution of my drive shaft, which I know I've got 311 gears in the back, so 11 revolutions here on the gear on the drive shaft is 3 revolutions on my tires. My tires are so big around, I know how fast I'm going now. And if I drive backwards, it's still going to count. So when I try and run my car in reverse, it's still going to count up the odometer, and I'm not going to be able to cheat like what's his name in thank you, Ferris Bueller.
Don't the car.
Right. Yeah. Don't push the car off the cliff. So you can do that with this. They can do the same kind of thing. They put an encoder in here, and as it goes, you get tick, 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 tick. But that's not real useful, right? Because you don't know if you ticked this way or if you ticked that way. I could have moved 10 ticks to here, or I could have moved 10 ticks to there. I don't know which way I moved.
Or just dithered around.
Or I could have just dithered around, and yeah, I got 600 ticks. Did that mean I just went 600 ticks in one direction, or did that mean, what did it mean? You don't know. So now we're going to go to what they call a quadrature encoder. And a quadrature encoder, they put 2 windows. Something like that. And they put a sensor here and a sensor there. And we'll call this A. We'll call this B. I didn't quite draw that right, but and what you get is A goes tick, like that, and B goes tick like this. Sure, why not? Now, if you look at this waveform, if I just say it's somewhere in space, I'm looking here, I don't know which one came first and which one came second. But if I notice in time that this is a rising edge, that means that this is already high. So this happened and then this happened. And now, so time is going this way. That means this is rotating one direction. If time is going the other direction, the rising edge happened here, and now that's low. And that tells me I'm rotating the other direction. So the system that I use this This is to measure a system that I built using one of those. So the system, the controlling system used these, Quadrature Encoder, to tell which way it was going and how fast and a bunch of other stuff. And then we just used these to verify it because that's just a regular pot and it was cheap and the optical encoders were expensive. Now, why would you choose one over the other, right?
Precision.
It's a big trade space, right? This is what I tell people. There's no such thing as the right answer. You've got a set of requirements, and you work your way there. In the case of, let's look at a scissor lift, right? I got a scissor lift. So in a scissor lift, I've got two arms that are here. I've got this one that's fixed. That can't move. And I got a wheel here. So what happens with the scissor lift is as I push this leg in, the scissor does this, right? Make sense? And up here, I put a firm fix on this guy, and I put a wheel on this guy, and I have a plate right here. So I can have somebody standing up here, right? And this is, you see these all over the place, guys doing windows and whatever else. He's got a control here with a lever on it. And now how do I drive this? What you'll see is the most common way that they drive them is a jack right here. Something similar to that. So now, and it's often hydraulic, so there's no rotating parts. So it's just moving up and down. So now I need a position sensor that can tell where I am in free space and doesn't have to require motions. So here I'm taking a linear space and turning it into rotational space. And I can measure how many ticks I'm going around and do that. Or if I use a screw, I can measure turns on the screw. So there's two ways that they do these. You don't use a screw this way because you can only go as far as the screw is long, right? And then you run out of screw. Hydraulics kind of neat because they can extend a lot longer in a more compact space and a lot faster. The other thing you can do here is you can lay a screw this way, and instead of this being a wheel, this is like an Acme nut, and you run your motor back here. Zzz. Now this is nice because you know exactly where you are and which way you're going if I was doing this, and so it would make more sense for me to use an optical encoder on this, but I'm not going to do that because probably I'm not going to do that because the forces that are required when I get all the way down, the force to lift that up is a cosine of this angle. And so, or actually it's 1 over the cosine, I think. So if I've got to lift, this guy weighs 100 pounds, when this is here, it's about 100 pounds force to lift him up, but when it's way out here, it's 3, 4, 5, 6, 800 pounds force to lift that guy up because you're way down here at the end of the stroke. And you're basically pulling on that. Do your old physics and statics problems from high school and college, and you can back that math out and say, oh my God, that's hard. Which is why we didn't use those on the thing that we were using these things on. That's just an example. You come down to it, again, there's a little bit of repeatability problem with this. Your 3D printers, you're running screws, you're running Acme screws all the time, you want to know exactly where this guy is. Step, 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 I can know exactly where he is in space and which way he's going so I can steer the head around and it's very precise. These guys have a, when you read them, the data sheet on this will be like plus or minus 2%. repeatability, and where you are in space can be plus or minus 1%. So you're not going to 3D print with plus and minus 1%. Your stuff's going to fall apart. Especially when you go way out on a long strip and then come back, and those start to add up if you don't hit a home switch somewhere to let you know where you are. So those are the easy things I was going to talk about tonight. The last thing I was going to talk about is this Pir sensor.
Before you leave
Okay.
encoders, talk about Baldwin.
Which Baldwin? The
Baldwin.
music company?
Yes.
What am I on?
And encoders, Baldwin is where encoders began.
Oh, really? I didn't know that.
Baldwin and the Baldwin Encoder Company, a small division that I think they're defunct now, but Baldwin made organs,
Yeah,
and
they still do, as far as I know.
they got into making an electrical
Oh, that's right.
organ.
That thing ran a gear
It
wheel
had a
against
tone wheel. And
Yeah.
the way they did waveforms was to have a wheel
That's right.
Wheel.
with patterns, circumferential or circular patterns at different annular distances on the wheels, and a magnetic pickup at first
To let
that
you know where it
watched
was
the
and it's
pattern, and that was to generate a waveform rather than RCL shaping circuits,
Yeah,
these
yeah.
sawtooths and square
Yeah, I
wave generators.
vaguely remember that. That you got a metal bar and you've got a toothed wheel.
It was toothed, and then they.
And this is spring loaded down basically, and it rotates this way so the metal bar goes.
That
like
was
that,
one,
and
then,
rings.
and then it moved to a magnetic pickup on a pattern on multiple patterns printed on the wheel, and then it moved to optical, and that became the Baldwin Encoder Company, the Baldwin Optical Encoder Company, and they were the kind of the premier guys along with measurement specialties.
This
They're
is-
Johnny come lately.
They're not. They're actually.
They're New England, aren't they?
So this is one of these things when you go and look at any one of these companies, they've been bought 37 times.
Yeah.
It's measurement specialties now. It was CE. Honeywell.
Really?
I want to say it was Honeywell, but I'm not sure. They sold off a line. I remember because it just changed over to these guys in the last 2 years. I don't remember who it was before, but that's what comes to mind.
Last piece of the thing here. If you've ever heard a Baldwin organ piece, and you heard somebody do something such that the entire frequency output of the organ went boo, it down. It almost Dopplered. It went down and came back up again. It's the tone wheel slowing down and speeding up again. So the whole sound generator just went.
That's neat. So I've forgotten all about that until you started talking about it. Okay, so this is, I'll hand that around. That's brand new. Probably won't let the smoke out of it. That's like $1.50, $2 part. That is a Pir motion sensor. That is what you see in when somebody comes walking in a door and the lights come on automatically.
Yeah.
It's one of those. Texas.
Building, Texas, you could
Do something with it, yeah.
run your phone or something.
Yeah, all of them have an amplifier in them. They're all amplified. You saw it. It's a 3-lead device. You've got power, you've got ground, and you've got signal coming back out of the thing. You can buy ones that are just analog, and so you can measure this thing and do your own stuff with it if you want. Excuse me. Those ones have a Schmidt trigger inside of them, which is, it gives you an edge. Something moved. I think something moved. Boom. Here's a high, and as soon as the movement stops, it goes away. So this thing, if there's a bunch of stuff moving around in front of it, it'll sit there and chatter. And if something comes in front of it, it'll give you a pulse and then die. And then when something moves again, then it'll give you a pulse and then it'll die.
Are these different type of material than might be used in bolometer?
It is,
Good word.
it's a real thing, a bolometer. It is, let's call it a type of bolometer.
Okay. I know the word, I don't know,
I
you know, skin deep knowledge.
a lot of, there's a couple of different kinds. The bolometers that I worked with when I did this much at an arm's length were actually a bridge. So it was on a die. We're talking down on a chip, right? And so you had silicon down here, and this was a this is usually platinum silicide, if I remember right, which is a I'm sorry, I'm having a complete brain fart at the moment. It's same thing a PRT is made out of. It's a thermistor. So what they are is a teeny tiny little bitty thermistor that's microns across. And as same process, as energy
As
comes
heat
in,
hits
it
it.
causes it to heat up. And you put a known source in front of it every now and then. Hey, this is room temperature, and I measure room temperature. And now it knows what room temperature is, and if it sees it get colder, it knows it. But you have to keep recalibrating it over and over and over. And if you listen to a thermal camera, you'll hear them tick.
It's an interrupter.
It's a beam interrupter, and it's a little piece that drops out in front of it and blocks the beam. And it's a little black body. It's black. It's got a cone, and it's whatever temperature the room is. And there's a little. Then there's actually a calibrated thermistor in there, and it says, "This is this temperature. This is this temperature." And you can hear them. They go click, click. There's a little solenoid that kicks them in and out. Little voice coil. And you can hear them. They'll click, click, and they'll go like click, click, and every now and then you hear them go click, 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 because things are changing, and it realizes things are changing, and it realizes it needs to keep recalibrating because it doesn't know what's going on. And if
So
you,
the tourmaline or whatever the heck it is
it's not tourmaline.
it's a different material.
It's a different material, so it's a little more sensitive.
And you're not trying to get an absolute number out of the PIR. You're looking for deltas.
Right, because this fades fast. It's leaky, so it gets that charge and then just starts bleeding the charge off. So you can't say, oh, I was at this charge, and now it changed to something else, and so I know there were delta charge doesn't always linearly correlate with delta T.
Okay.
So or delta energy on the thing, or however you want to look at it.
I get it. Yeah.
So now, okay, where were we? We were at the heater kicks on and warms up the wall there and blows heat on it, and it kicks on. So the patent is this, basically.
Okay.
And this one's behind a shield. This one's hidden from view. It can't see. And now, as temperature rises and falls, these two pieces that are cut
You're trying to
As-
temperature
as-
compensate this thing.
as close to exactly the same as you can, that are right next to each other, getting the same thermal energy from the room on them, are sitting there drifting together in temperature. And if we do Kirchoff's voltage law, right, this plus this has to sum to 0. So if they're both the same temperature and they're both the same voltage being generated, then this is a 0 voltage coming out. And now my lens, I've got this piece and that piece right there. This one's behind a shield. My lens focuses in like that, and only that one gets heated by the scene that it's seen in front of it. I don't think you can buy one anymore that's not this. It's not differential. I could be wrong.
This one you think is different?
I'm pretty sure that's differential. I did quite a bit of research into these. They might not be $1.50 or $2.50 now anymore. I bought these almost 10 years ago. See, doesn't say the cost on here. This is made by Panasonic. They still make these. I don't know what the cost is. I made these specifically as a motion sensor, a thermal motion sensor, to pick something up and let me know something was going on. But that's how a PIR sensor works. And that has been an hour. And I guess I planned these three things pretty well tonight. So now, any questions, any feedback? You want to throw rotten fruit? Get that on YouTube. People will laugh. I might get 1 million hits and make a buck. Have I bored you all to tears?
A bit about the crystal moving makes me, probably might be the same thing. In the 80s, Volkswagen came out with a knock sensor, which is a little block.
Mm-hmm.
And you had to torque the bolt to a specific torque, and it sensed there's a
ping.
knock. And I guess that triggered on in with the ignition to say, okay,
We need to change
it's
the
got to
timing.
be this cylinder, and it retarded that cylinder.
That's cool.
But that was, I think, generating a frequency.
Yeah, that's how the knock sensors work. The ping sensor. It hears it pinging. Yeah, this is exactly how they work. Far as I know. I didn't know that they went that far, though. I didn't know they retarded a single cylinder. I thought they just retarded all of it.
And knowing Volkswagens, you can unthread the components and move it to another Volkswagen, and it
Might work.
It's been done. Volkswagens are known for that. That's why I own a couple of them.
Do stove spark igniters have anything other than the piezo in there? Are they a coil as well, or? I mean, this is a little button that I push down, and at some point it passes a pawl or a catch.
Yeah, that's exactly how it works. The piezo voltage is in the thousands of volts.
Yeah, I mean, it's
You don't need a
that long. Yeah.
You don't need to step up on them. It's just a wire off the crystal. It's a big crystal, and you're really hitting it hard. The pounds per square inch when that thing smacks on there is probably in the hundreds or thousands of pounds per square inch.
Is it hitting it, or is it releasing it?
It's striking it, I think. You're coming in. You got this button,
Probably like a, what is it?
and you've got a flat spot on the bottom. It might have a little dimple on it, but you're smacking into this piezo material, and one side is grounded to the case, another side comes out to the sparker, and
It's the center punch tool with a spring in it, probably.
it sort of is. You got it exactly right. There's a little breakover pawl here on the side with a spring somewhere in here that's, I guess it'd be on this side maybe. It's trying to keep it from going, or actually maybe it's right here. Makes more sense. So you got a spring right here. Yeah, that's right. Because the neat thing is, the harder you push on it, the harder that spring pushes back on you.
Yeah.
Until you finally get to the point where that force here overcomes that spring force, and then just BAM! It just punches it right square into kisser.
And I mean, you were talking earlier about using piezos as a microphone, which I think about as millivolts to maybe a volt on
Yeah,
on
because
a really
you're
loud
not
day,
you're not smacking
but
them hard.
not a kilovolt
Right, because you're not smacking them hard.
or
like
several.
Yeah. You're smacking that hard. You're smacking that really, really hard. And in fact,
Aren't they layers?
no, I think they're single crystal. I might be wrong. It might be multiple. I've never taken one apart. I don't know. There's actually some neat work
I
going
mean,
on.
the piece of crystal is in itself multiple layers?
Well, it is a crystal structure.
Okay,
So
all right,
if you want,
all right, yeah.
there's some.
I guess that comes with the party, you know?
I mean, it depends on how you look at it, I guess. But yeah, there's with the piezo, there's some interesting things that have been going on with adaptive optics. Why do I put telescopes in space? Right? There's no air.
No distortion.
Number one, I can see things that aren't being blocked by the atmosphere.
Temperature differences.
It's not temperature differences. There's two.
Still got that.
There's two things I care about. If you look at,
Gravity.
that's actually, yeah.
Distortion on weight. And
Yeah.
things like that.
Yeah, there is. But if I look through the atmosphere, I see this. And this is not at all right, but this is,
Modulation transfer function?
no. This is transmission. With this being like, 99.99% of the light goes through. And this is the frequency of the light, the color of the light. There's holes. There's places where I can't see through the atmosphere. There are certain bands of the atmosphere where you can put all the energy in the world and it won't go that far. Carbon dioxide band blocks certain wavelengths of light. Hydrogen band blocks certain, which is the water band, the hydrogen-oxygen lines. These things that we look at the sun and we say, oh, we know what the sun's made out of because we see these lines. Well, those lines are really bright because they're coming from a star, right? That's right there. But things, if I want to look at a star that's 10 light years away, there's not enough energy to make it all the way through there. And I might be looking in a band that's only in the 20% region. So bands, I want to get my telescope up above it, which is why we go out to Kitt Peak, which is why we go to that high desert in Argentina, whatever the heck the name of that is. That's why these huge astronomical observatories are up on top of mountains, because there's not as much atmosphere above them, so you can see more.
Well, you also have a lesser degree of refractory distortion.
Yes. So
due to the dynamics of that
which
atmosphere.
is where I'm going. So, but I wanted to touch on this and get it out of the way, so that I'm not telling a complete lie. I'm only telling partial lies. So, you're driving down the road on a hot summer day, and you see water.
Heat waves.
You see heat waves, you see water. What you're seeing is, I have a hot surface. We talked about this at the very beginning of the class. I'm going to actually go around and close the loop today. The air's hot, the air spreads out. The air is actually thinner right down here by the surface than it is up here. Because the cool air is trying to come down, but there's this huge hot piece of asphalt there that as soon as any air gets on it, it's lifting it right back up, right? So you actually have sort of a barrier layer there where the air is thin and then it's thick. And there's a difference in the index of refraction. So as light comes in, it does that. The water you see is actually the sky. It's the blue sky. If it's blue, if it looks kind of white, you're seeing clouds, you're seeing whatever is in front of you. And if you notice, you get in the right places, short enough distances, you can see the car in both. You can see headlights on the road, you see double pairs of headlights. If you pay attention, you can see the upside down image in this reflection. Now, thin air, thick air. I got 100 miles of air up above me that's all sorts of different temperatures and doing all sorts of different weird stuff. And there's winds blowing. So when wind blows, clearly there's a pressure front there. It's not very much. If the wind blows here, it's not going to distort my image of you in my eye. But if you were 100 miles away and I was looking at you, it would. And that's why stars flicker. That's why Twinkle Twinkle Little Star happens, because the atmosphere is doing all this boiling and roiling and this refraction is going on and causing them to twinkle. So the game they play these days, sometimes, is you have your telescope looking up at the sky. We'll just do it that way. So the light comes in, bounces off, comes back here to a focus. And that's where I put my detector. Now I put a beam splitter right here, say, and I put a laser right here. This laser sends a beam out, and I make it a color that will reflect off of certain layers of the atmosphere. And so when this leaves here, it's a round dot. When it gets up here on the top of the atmosphere, it reflects, and instead of being a round dot, it's got some sort of stupid shape like this. And then it comes back down, and I can see that here in my detector. So I can say, this is the effect that the atmosphere is having on this beam of light going through the atmosphere. Now, obviously it's double the effect probably because it's up and back. But now what they do is right here on this mirror, they put a bunch of piezoelectric stuff, and you say, I know that should be round. And you start adjusting the voltage on those piezoelectric crystals to actually deform the lens. And they're actually causing the mirror to bend a teeny little bit here and there to correct that optic, and that is adaptive optics. That's how adaptive optics work in a telescope system. The biggest one I've ever heard of is about that big around. I did see a presentation where they were talking about some really, oh God, I can't talk about that. I don't know if I can talk about that or not. I better not talk about that. I've seen some nifty things that people are talking about doing with some telescopes. Actually, I can talk about that. So the problem is, I've got all this glass and all these things here. So here's a trade-off, right? A mirror is actually a light collector. It takes a huge amount of light, a huge amount of area, right? We talked about this a little bit before. If I've got a point source here, a star, the sun, light comes off like this, right? Only these are spheres. The closer I am, quit that, the more energy there is. So as R goes out, this same amount of energy was here is now spread over a bigger distance, is spread over a bigger distance, is spread over a bigger distance. And so the whole idea of a telescope is to take as much light as possible and focus it down into as small a spot as possible so I can see the dimmest thing possible. So a big mirror, the Hubble telescope's mirror is about 3 meters. It's not quite a 10-foot mirror, or it's around a 10-foot mirror. That is a big hunk of glass. If I look at some of the stuff they're building out in, and it's up there, it's a great big frickin' hunk of glass. If you look at some of the stuff that they're doing adaptive optics, but it becomes the weight problem, right? I can't build a piece of glass that's much bigger than about 5 meters that's smooth. So that means I need to break it into pieces and start building these big 5-meter pieces.
And align the optics.
And align them and do all this stuff. Now I do as best I can, and then I have an adaptive optic that sits there and takes into account how these things are all screwed up, because as they heat and cool, they're going to move a little bit differently. As the wind blows, this one's going to vibrate a little bit or whatever. And now I've got this other optic, right? So I've got all these things going on, multiple sets of adaptive optics to correct this thing. And it's big, it's huge. If I could make a a mirror that's as big as the Earth, I'm exaggerating. If I could make a mirror that's as big as the Earth, I could see a lot of cool stuff way out at the edge of the universe. But I can't, there's not enough space on the ground, it'd be too heavy. There's all sorts of engineering problems that go on with this. But if I could put it in space, it'd weigh nothing. But the problem is that if I put it in space, well, it costs a lot of money to launch something into space, right? And I've already said I can only do like maybe a 5-meter mirror. I think the fairing on the new EELVs or maybe the Teslas, maybe a 10-meter fairing. So the biggest thing I can send up is maybe something that's 30 feet across. And when it goes up, it's going to get a hell of a ride. That's not a smooth ride on the way up. You're riding a bomb. 200 and some odd dB of acoustic noise rattling the hell out of everything. If I got a bolt that falls out of this on the way up, that's a problem because now it's going to fall apart. How do I assemble this thing in space? That's a real problem. But what if I put a balloon in space? What if I took a Mylar party balloon with almost no air in it? One side's clear, and the other side's got the Mylar, got the aluminum deposit on it. And now I pop this thing into space. And just let the little bit of air that's in there blow it up like a balloon. It doesn't take a lot of air because you're in a vacuum, right? Now I get this giant party balloon that opens up like this, and this side's clear, and this side's shiny. And now maybe I put a little satellite out here to be the receiver on it. So now I can have something that's 100 yards across, and the light comes in, bounces, I receive it here on this little bitty detector that's, well, probably about that big, and then I beam my images to Earth. Now it's a problem about a small thing
Compensating for,
that has to, well, now you get into this whole thing of formation flying. That's hard. And keeping a good distance. And, you know, this thing's wanting to deform and whatever else, because there are winds in space that will, I mean, this is a big enough thing, it's going to have drag, even on that small amount of air, as it flies along. So, one of the things that they were looking at was if you do a deposition layer of a piezoelectric material on this, and then up here I put an electron gun out of an old TV tube. And now I look at my image and I say, that should be round, and it's not. I do my algorithms and I say, oh, that means that that part over there has a funny wrinkle in it. I shoot an electron gun at it, it puts a charge on it and causes it to bend. And now this whole 100-meter thing
becomes an adaptive
optic. With another one here to do the fine corrections.
Oh, that's hysterical.
That is a very clever idea. And that is perfectly doable with today's technology if you're willing to throw the money at it.
That's good.
The last I heard, they were investigating some of, can you make this? Because it's one thing to say, oh, I'm going to make an aluminized Mylar balloon, but now I'm going to fold it up in origami into something this big. And is it going to cause splits in the material and whatever? And is it going to act the same way that I want it to act? But now, but here now you're talking a 100-meter mirror that's, I don't know, $50,000. You know, or 100. You know, even if it's $1 million, that's even if it's $100 million, that's a bargain.
Yeah.
That is a hell of a bargain.
Yeah.
Because the mirrors that they're making for these things are $10-20 million a piece.
Let alone how much it costs to put them there.
Let alone how much. I'm even talking here on ground state, on ground stuff.
Yeah.
Some of the stuff they gave a presentation at a meeting October. It was the Korea KSTM array. Korea. They're looking for exoplanets, and the way they were doing it, it was 30-meter mirrors. There was 3 of these things. one in Argentina on that high, one in Kitt Peak, and one in Australia, because those are all right on the equator. 3 of them gives you perfect coverage. Each one of them was a 30-meter mirror.
That's a big mirror.
It is a big mirror. I mean, it was segmented mirror. I think it was 1, 2, 3, 4, maybe 6 segments, like James Webb Telescope is supposed to be.
Jesus, you know, you build a big, huge mirror like that now, if you think about it. Start from nothing, 3D print it, let it keep getting bigger and bigger and bigger and bigger and bigger, and then grind it.
It's not good enough and it's not strong enough.
Yeah.
When you
Anyway, just keeping molten glass, adding it more and more and more and more and more and more. And
it won't work because it creates imperfections below the top layer of the glass.
Yeah.
Where that bead lays around, there's a second surface.
Yeah, it's not tempered either.
What one of the outfits who makes these big mirrors is University of Arizona out in Phoenix, I think, and they have this really neat kiln. I remember reading about this 15 years ago. This instrument they put up, they made 2 5-meter mirrors. I think it was for this instrument. It was a stereo instrument. It went up into space. It was a NASA job, and it went out in these 2 mirrors folded out like this. And it was some sort of an interferometer type thing. And what they've got, they go out and they buy the glass in chunks. And they go through and they look at every one of them under a microscope for imperfections. And if it has any kind of imperfection, they throw it away. Which I don't exactly understand because they're going to melt it anyway. And they have this telescope blank, which or the inverse. So they're honeycombed on the back to lightweight them, right? They're this thick, so they're not that lightweight, but I think it's silicon carbide, hexagons all over the place they've got, and they go in and they spill these glass chunks all over and fill it up, and then there's a clamshell lid that comes down, and I think it's got heaters underneath, but I know it's got big heaters on top, and it heats it up, and the whole thing slowly spins. It's like 1 revolution per minute. And what that does is, as the glass melts, the centrifugal force pushes it out, and it makes a natural parabola. And the baking process for these mirrors is like 2 months, 3 months.
Yeah.
Slow heat up, slow cool down, so that you don't cause imperfections. Then they get it out, they pop it out, and then they go over it and meter it, I think is what you call it. I can't remember it. It's
Very, very, very fine grain polish.
yeah, and so
that glass doesn't expand or contract with temperature.
it does. So you have to know the temperature of it, and you have to keep it at that temperature. So when it goes up into space, it's going to have heaters all over it, and they're going to be keeping things within, a 1/4 degree of where you want them all over the place. That's a thing. It's a hard thing, believe it or not. We talked about that a couple of weeks ago, about how hard it is to do that kind of stuff. There's an interesting effect, and I can't tell you the physics behind this because I don't know optical physics. But the smallest, when you have a lens or a mirror, I'll make it a lens, and I put a point source out here in space, a star. The light comes through, and it makes not a spot, it makes an airy disk. And in this first ring right here, the energy in here is like 98 or 99% of all the energy in that spotlight. How small you can make that is a function of the diameter of the disk and the wavelength of the light. if there's any roughness here, you cause this disc to expand. So let's assume that we've made it flat over, you know, some level of flat, but it's the same flat all over. There's no comas, there's no astigmatisms, there's no, but you know, just down at the level below what I can polish, there's some random waviness. The bumpier that is, the bigger this blur spot's going to be. So your first area disc basically goes out and out. This, by the way, if you cut that in half, is a sync function. That's sine x over x. And if you look at it here on the plane, it looks like this. And these are where the area discs will show up. So the bigger this is, the smaller that gets. But the rougher it gets, the bigger it gets. The bigger it gets, the more light I get in, though, so the brighter that spot is, which is a good thing. It's interesting, what they'll usually spec a mirror to, this would be, I think, a first surface mirror, or actually the reflector might be the first surface mirror, but what they'll do is they'll specify them within a RMS of the wavelength of, they'll usually say it's like a 5th lambda or an 8th lambda. So lambda is the wavelength of light. The light they use is red light. A good mirror is no less than 1/8, or no worse than 1/8. A really good mirror is down around a 10th or a 12th. I've seen some 15ths and 20ths. But that's at red, and so blue is a higher frequency, so what's smooth at red is less smooth at blue. So even though there's this project we worked on one time where the customer would not give us the information we wanted. We want you to build a telescope that does this, and we need to have this, this, and this at these different frequencies of light, and we want the pixel size subtended onto the image to be so much. Well, okay, tell us what the wavelengths are. Well, we don't want to tell you what the wavelengths are because those are our proprietary secret sauce. Well,
Can't help you much.
How about frequency?
no. Well, there's this huge go around. We don't want to tell you this. Oh, we don't want to tell you that. Oh, and so it became this huge exercise because, well, crap. We need to tune this to the work. It was pushing us off to we have to design it for the worst case possibility, right? Oh, you want your blue light to be in a spot that's teeny tiny. And so that means that because of surface roughness, I have to make the mirror huge to overcome the surface roughness. But it was an interesting thing. What we found out was it sort of all canceled out. If I designed for green, that one that's right in the middle of the spectrum there, red dots would get smaller to a certain... They would get bigger because the wavelength is longer. But blue dots wouldn't get any smaller because they'd start getting blurry and they'd start to spread back out. So it turned out, in the end, we did all this math and spent, I don't know how much dollars, a lot, to find out that, you know what, all I needed to really do was design for green, and I was pretty close to where I needed to be for all of them. I'm boring you?
No, I gotta go down to Deal, so.
Oh God, that's a long haul from here.
That's why I work down there too. I'm tired of working up here.
Actually, I'm thinking I'm at home. You're not quite as far as you are from. I'm another hour, almost an hour north of here.
Where's that?
Pasadena. Ooh. So yeah, you're about an hour north of where you're going. So
Next time maybe I'll bring my device.
cool. Let's see if we can let smoke out of it in a bright and
It's
spectacular
not,
fashion.
It's not assembled yet. I got the bus bars made and I got all the parts. I need 100 watt.
Let me turn this off. Oh, we're gonna start boring people online.